Greetings everyone, this is Mr. Mull. What I'm going to do today for you is I'm going to work through the weight challenge question, and it will help you look at force diagrams in a more complete manner. So I want to go back to that weight challenge from the What's Up with Weight Lab, and I want to look really closely at how we can use force diagrams and vector equations to solve for unknowns when we're looking at objects. So here's my situation. Remember from the lab that we had this hanging mass and this forceometer, and you were holding it down, and I gave you this question asking you how much do you need to hold it down, and just kind of like just a quick sketch of things. Recall that you were holding down force of push on the object, on the forceometer by my hand, and the forceometer had a little bit of mass, so the earth was pulling on it. Force of gravity on forceometer by the earth. At the same time, you're looking at that object, there was a string attached to it, pulling it vertically. Force of tension on the forceometer by the string. And then also, you pressed the forceometer up against the surface of the desk, and there was this normal force. Force normal on forceometer by the ring stand. So looking at all of the forces involved, I just drew these arrows any random length, but we're going to try to figure out how long should we draw them. How can we know for certain how long those arrows should be? So what's really important about this situation is that the object is not accelerating. In fact, the whole system is not accelerating. So that tells us that in any given direction, vertically or horizontally, that forces are going to have to be balanced. So when I look at all my vertical forces and I compare them to all my vertical forces in the opposite direction, all those positive forces plus all those forces that are acting negative are going to end up canceling each other out. So if I swing all those negative forces to the other side of this equation, I know that all of these forces up here are going to have to be equal to all the forces down there. Okay, so I'm going to ignore the negative sign for right now, and I'm just going to set them mathematically equal to each other. So if I write a force equation, the normal force on the forceometer by the ring stand plus the force of tension on the forceometer by the string have to add up and equal to force of gravity on the forceometer by the earth plus the force of push on the forceometer by my hand. And so this is going to be an equation for my vertical forces. Now horizontally, there's no forces pushing or pulling horizontally along that other axis. So I'm purely looking at along the perpendicular to the surface axes. So if I were to interject a coordinate system onto this problem, I would choose perpendicular and parallel. You could choose X and Y if you'd like, and those would be my axes. So I don't have any horizontal forces, I don't have to worry about it. So what I want to do now is I want to find a way to solve for this push here. That means I need these other three. Before I get too far ahead of myself, I also want to look at the fact that I need a force diagram for the hanging mass, which was the simpler situation. Now that hanging mass is going to be two forces. Okay, we had the force of gravity on the mass from the earth, and then we had that rope attached to it, the force of tension on the mass from the string. And because the object was accelerating, this has its own little force equation. Force of tension on mass by string is equal to the force of gravity on mass by earth. I know those are going to be equal because the object is not accelerating vertically. So I'm going to use those equalities that we've learned how to set up and make a little equation for those. Once I've done this, now I need to make all of this quantitative, and I need to make the arrow size correct between these two force diagrams. So I need to solve for some things I know. The point of the lab was to figure out how we can find out what is the force due to gravity. So this force due to gravity of this pull let's start with my hanging mass. That is equal to my weight. And that's equal to the mass times the gravitational field strength for the object. So when I plug those in, for my 4 kilogram mass, I had 4 kilograms times gravitational field strength of 10 newtons per kilogram. That gives me a value of 4 newtons. So 4 newtons is going to be applying to all of these 4 newtons. So now I can plug in and make this quantitative. 4 newtons. So we can actually put a value on there. Those are going to be equal to each other. The other thing I can do is, looking at this other equation, I can solve for the force due to gravity here. That's equal to the weight. That is the weight of the object, mass times gravity, gravitational field strength. And so I plug in the mass of this object, 0.1 kilograms times 10 newtons per kilogram. Newtons per kilogram. And I'm going to get a value of 1 newton. So the Earth is pulling on my forceometer a value of 1 newton. Okay, 1 newton. So I know one of these things, and now I need to find 2 of the other ones so I can solve for my unknown. I need to solve for this. So I'm going to look at the problem, and it gives me some information. It gave me the fact that there's 1.5 newtons of support force beneath the sensor. So what that means is that the ring stand here is providing 1.5 newtons of force as those atoms are getting scrunched, or those surfaces are pressing together. So that normal force acting is 1.5 newtons, and I can plug in that value. Last but not least, we need to find one more. Looking at this tension here on this other diagram, because those strings are attached, because both of these because this is the same string, that force of tension is going to be felt along the entire string. Just like if I have 2 ends of a rubber band, both hands feel the same. That pulley is just redirecting that force. So assuming this string is massless, we're going to say and assume that the tension is felt the same throughout the entire string or chain or whatever. So that means that this 4 newtons here for the tension felt on a hanging mass is the same as the tension felt here. So this is 4 newtons. So I can go ahead and plug this in. 4 newtons. Now that I have 3 of the 4 values, I can solve. 1.5 plus 4 equals 1 newton plus x. Solve for your unknown. That force of pull on the forceometer by the hand is going to be equal to 4.5 newtons when I rearrange everything. So now I know that this is 4.5 newtons. This was 1 newton, this is 1.5 newtons. And the last thing you can do is we can go back and make qualitatively correct force diagram. So as I'm drawing those arrow lengths, I could redraw that whole diagram. We're going to have 4 newtons of force, which is going to be not quite as long as the 4.5 newtons of force of my push, and then we would have 1 newton of force, and then we would have our a little bit longer at 1.5. So you would do your best to make this qualitatively as well as quantitatively accurate. And I'm not going to bother with the quality marks here because there's a lot going on. Okay, but you could make a force equation, and that would be more helpful than using my quality marks for this type of problem. Well, this was the force challenge, and I hope this was helpful.